in section 4.2 we're going to learn about the derivatives of exponential functions. And the natural exponential function y equals e to the x is really important in calculus. I call it a calculus's favorite function because it is the only non-zero function that is its own derivative. So f prime of x is equal to e to the x. Okay, and what I want you to do in example 4.5 is to imagine what e to the x would look like if it were a polynomial function. It's not quite a polynomial function, but if it were, it would have to have this following property, that when you take the derivative, you get e to the x back, right? So if the polynomial were to start 1 plus x squared over 2, then when you take the derivative of 1, you should get 0, right? And then when you take the derivative of x, you should get 1. Okay, so e to the x should start off like with 1 plus x, right? And then the question is, what do you take the derivative of to give x? Because that should be, this term right here should be x, right? Well, to do that, you know you have to take the derivative of x squared over 2, or you take the derivative of x squared to get an x power, and that would be wrong because you'd have 2 times x. If you just took the derivative of x squared, you would get 2x, and we'd be off by a factor of 2. So that's why it's x squared over 2 here. So the point is that the derivative of this thing now is exactly x over 2 times 2. Okay? And now the question is, what do I need to take the derivative of to get x squared over 2? Well, because I know this term right here should be x squared over 2, right? Because that was the first term right there. Well, what do I need to take the derivative of to give me that? I need to have x cubed, and then that wouldn't be quite right, because when I take the derivative I get 3x squared over 2, so I need to take x cubed over 2 times 3. Okay? And if you check that, when you take the derivative of that, you do get 3x squared over 3 times 2. The 3's cancel, and so you're left with the x squared over 2 there. So that worked out. But then that means that this next term over here has to be x cubed over 3 times 2, or x cubed over 6. And now the question is, what do I take the derivative of to get x cubed over 6? Well, it must be something like x to the 4th over 6. But then again, if I take the derivative of x to the 4th, I'm going to have a 4x to the 3rd over 6, so I'm off by a factor of 4 again. So I need to multiply by 4 times 6 on the bottom. Or maybe I should write that as 4 times 3 times 2. Okay? So you can check that if I take the derivative of the red thing, I do get x to the 3rd over 6. That means I need to tack this on over here, x to the 4th over 4 times 3 times 2. Okay, well then what do I take the derivative of to get x to the 4th over 4 times 3 times 2? It's going to be x to the 5th over 5 times 4 times 3 times 2. And then that means that this must go over here because these two functions are supposed to be equal. Okay, so I think you can start to see the pattern now. In general, the nth term is going to be x to the n over n times n minus 1 times n minus 2 times n minus 3 times n minus 4, and so on. And there's a special notation for that. That's n factorial. N factorial means you take n times n minus 1 times n minus 2, and you keep subtracting until you get down to 1. You multiply all those together. Okay? And so that is exactly the formula for e. It's an infinite sum. It's a polynomial with an infinite number of terms. Okay, so you can't just stop at any n. You have to keep on going. But this gives you a really good idea of what e actually is. The number e to the 1 should be this polynomial, or this infinite polynomial, with 1 plugged in. So if you plug in 1 here, you're going to get 1 plus, if you plug in 1 for x, and then 1 squared over 2, and then 1 cubed over 6 plus 1 to the 4th over, what is that, 24? if you add up those first few terms, you're already going to get a number that's close to 2.72. And if you add like the first 10 terms, you're going to get really close to 2.72.